Okay, so for our first one here, 45 kilograms going into pounds. Yeah, 45 kilograms over 1. And our conversion factor, kilograms are going to go on bottom, pounds are going to go on top, and our relationship is 1 kilogram is 2.2 pounds. So the kilograms cancel out. 45 times 2.2 is 99 pounds over 1, so it's just 99 pounds. $18 gallons going into liters. So we make it 18 gallons over 1. Gallons go on bottom, liters on top. 1 gallon is 3.79, I believe is what the book uses. Gallons cross cancel out. We have 18 times 3.79. 68.22. So 68.22 liters. Now, if this were a technical math class or a little bit more advanced math geared towards engineering or something along that line in design field, we would probably talk about significant digits and how we can't leave that as 68.22. But for our purposes, we're just going to go ahead and leave it like that. The next one, 8 inches going into centimeters. So 8 inches over 1 again. Make our conversion factor, inches on bottom, centimeters on top. 1 inch is 2.54 centimeters. So 18, well, the inches cancel out, obviously. 8 times 2.54 is 20.32, so 20.32 centimeters. 72 centimeters going into millimeters. This is just using the chart. To get from centimeters to millimeters on the chart, it's 1 spot to the right. So my decimal point has to move 1 spot to the right. I have to fill in a 0. So that's 720. 13 feet going into inches. So that's 13 feet over 1. And I realize most of you can make this conversion without having to do a conversion factor. But we're going to do it with a conversion factor anyway. 1 foot is 12 inches. The feet cancel out. 13 times 12 is 156 inches. You know, 1 times 1 is 1, so it's 156 inches. This next one, 144 ounces, going into pounds. So it's 144 over 1. Ounces are going to go on bottom and pounds on top. We have 1 pound is 16 ounces. The ounces cancel out. I've got 144 times 1 pound is 144 pounds. 1 times 16 is 16. So 144 divided by 16 is 9 pounds. Anybody have all 6 of those right? Yeah, use the cell phone converter? Yeah, well, as long as it works. I will warn you on some of those cell phone converters, there are certain, I've talked about how different countries standardize their units at different times, so they might be slightly different. Unless your settings are absolutely perfect on the cell phone converter, there are some that will be just slightly off when you do them. Like you might put in 3 quart or 3 pints, and instead of spitting out 6 cups, it might spit out like 6.28 cups or something like that. So be careful with those. Make sure it's set to English standard, or American standard, I should say, U.S. standard. Okay. So like the other thing to be aware of with the measurements, we talked about it just briefly, is if we have something like 3 square feet going into square inches. This is no longer going to be 12 inches in a foot because it's not inches and feet. It's square inches and square feet. So 3 square feet over 1. Square feet go on bottom and square inches on top. 1 square foot. Does anybody remember how many square inches are in 1 square foot? Remember, it's 1 foot by 1 foot, so 12 inches by 12 inches. 144 square inches. Good. So the square feet cancel out. It is 3 times 144, which is 432 square inches. If I am going from cubic yards into cubic feet, again, it's not going to be just 3 yards per foot because it's not yards and feet. It's cubic yards and cubic feet. 1 cubic yard. Does anybody remember how many cubic feet are in a cubic yard? Well, it's 1 yard by 1 yard by 1 yard, so 3 feet by 3 feet by 3 feet, which is 3 times 3 times 3, 27. There you go. Yards cancel out. We get 135 cubic feet. So 5,184 cubic inches going into cubic feet. We're going the other direction now, but it's also cubic instead of squared. So cubic inches over 1, cubic inches on bottom, cubic feet on top. The larger unit is the feet, so I'm going to put 1 cubic foot. Does you remember how many cubic inches are in a cubic foot? 12 times 12 times 12, exactly. Which is 1,728. So the cubic inches cancel out. 5,184 times 1 cubic foot is 5,184 cubic feet. 1 times 1728 is 1728. That divides out to give you 3 cubic feet. Or one more example, 54 square feet going into square yards. Square feet on bottom, square yards on top. Yards are bigger, so it's 1 square yard. It's 3 by 3 or, careful, 9. 1 yard is 3 feet, so 3 times 3 would be just 9. So, square feet cancel out. 54 times 1 yard is 54 yards squared. 1 times 9 is 9. 54 divided by 9 is 6 square yards. Any questions on those? It's just a matter of remembering that they're not the same conversion factor and then figuring out what the right conversion factor is. Okay, so tonight we're going to start talking more about some geometric stuff. We went over the measurement so that we can measure dimensions of things and do some calculations off of them. We'd mentioned earlier that all geometry comes from this object right here. It's the simplest geometric figure that you can have, and it is a point. It is just a location, and it has 0 dimensions, no dimensions at all. Dimension is just a measurable direction, is what the definition of a dimension is. So it has none. We created lengths by taking that point and moving it in a single direction. That creates a length. And the length of that is equal to the distance that it was moved. This is now one-dimensional because measurable in a single direction. The point has been moved in a single direction. This is what is called a line segment. In practice, a lot of people call that a line because for practical uses, that's the only type of line we can use. An actual line, of course, goes on forever in both directions. In reality, there isn't much use, much practical application for something that goes on forever in both directions. Most of what we work with have definite endpoints. So when you hear the term line, generally we are referring to a line segment. A variation of that is to take that single point and take off in a single direction and keep going. That is what we call a ray. Now to name these figures, a line segment, let's say this is point A and point B, we could name that segment AB or segment BA. The abbreviation is just a little line segment above them like that. For the line segment, it doesn't matter which way we name it. For a ray, however, let's say this is point A, B, and C. This could either be called ray AB or AC, but A must be the first letter because that is the starting point of the ray. That's the end point. We start with that end point and we move towards the arrow, towards the infinite direction. So that could be AB, ray AB, or ray AC. Or the first letter has to be A, the second one can be any other point along that ray. Well, what we're most concerned about creating tonight are figures that look like this. We have that point, we'll call that point D, and we create a ray by going in a single direction away from it. I'm going to put a point on here, point E, so that is ray DE. Now I'm going to go back to point D again and move in a slightly different direction, creating another ray. I'll put a point on that ray called F, so that's ray DF. What we've created here is what you'd refer to as an angle. To name that angle, that's the symbol for an angle, we name one side, we name the vertex, which is the point, the common starting point, and then we name a point on the other side. It doesn't have to be in any particular order as long as the vertex is in the middle. So this is angle EDF, could be called angle FDE, or if there were other points on either of those sides, we could change those in as well. The size of an angle. The measurement of an angle, measuring the size of an angle, has changed through the years. There's some historical value to it. Originally, back when navigating was common, in your navigational directions, 0 degrees was your east direction, 90 degrees was your north direction, 180 degrees was west, 270 is south, and then 360 was back to 0. And most people were pretty familiar with navigation because it was pretty commonly used. So the size of an angle was measured by, well, first of all, you could define the direction of a ray based on this navigational grid. So the starting point was always the center, and let's say this goes across here at like 26 degrees. So that is the direction of that ray is a 26-degree ray. Then you'd have another ray. Again, the vertex or starting point has to be at the center of the grid. Comes off at a different angle. Let's say that angle from here up to there is 61 degrees. So that's a 61-degree ray. The angle formed by those two rays is the difference in their direction. 61 minus 26 is 35 degrees. So that angle is a 35-degree angle in between them. Well, through the years, people have become less familiar with navigation, so that definition has been more difficult to deal with. So what they've done is just kind of gone down to benchmarks. If we start and go in a complete circle, how many degrees is that? 360 degrees. If we turn and go completely back in the opposite direction, how many degrees is that? 180 degrees. And you can find that simply because it's half of 360. If we turn to go in a square corner like that, how many degrees have we gone? 90. Again, that's 1/4 of a complete turn, so 360 divided by 4. all of our angles have been defined now as a fraction of a complete turn, as a fraction of 360 degrees. So when I look at this angle here, if I tell you that that is 56 degrees, all that's saying is that is 56 3/60ths of a whole turn. So let's look at some definitions here. This one here that is a quarter turn, or what we call 90 degrees, is called a right angle. That name comes from the fact that in so many different applications of angles, that is the correct angle, the right angle. When you're building a house, that's the right angle for the walls to sit at. Intersections on roads, that's the correct angle, the right angle for the roads to intersect at. And all sorts of applications where that is the correct or the right angle. So that's where that name came from. Anything that is smaller than a right angle, less than 90 degrees, is referred to with the name acute. Exactly. Now think of it like this. Things that are acute or small, acute angles are smaller than 90 degrees. That's how you remember it? Because it's cute. An angle that is bigger than 90 degrees is obtuse. I don't know if you've ever heard the terms, you have an acute thinker or an obtuse thinker. An acute thinker is somebody who focuses in and sees just a very narrow piece of it, but can focus in and see every detail of that narrow little piece, which is good in some applications. An obtuse thinker is somebody who sees the wide angle and sees the big picture, but not necessarily the little details of any piece. Okay, so based off of those, we're going to use those when we start naming triangles as well. But let's look at some special angle relationships. So if we have an angle here like this, let's say that one is 31 degrees. And we construct another angle. We come back to that vertex, that same starting point, and we construct another ray off of it. We have now constructed another angle. Let's say that angle is 46 degrees. These two angles, one, share a common vertex, and two, they share a side. So that makes them what we call adjacent angles. And here I only have two angles that are adjacent to each other, but I can have 3, 4, or more angles that are adjacent. They have to share a common vertex, and they have to share a side with one of the other angles. But the nice thing about adjacent angles is they are what we call additive. So if I wanted to find this whole big angle here, all I have to do is add together the 46 and the 31. You get 77 degrees. That's that larger angle. Likewise, say I have an angle that I know is 116 degrees. I put an angle in here that is 44 degrees. How do I find this angle up here? Well, if I call that angle x, I know those two angles, x and 44, are adjacent. They share a common vertex, and the brown side there is shared by both angles. So x plus 44 has to equal 116. So how do I find x? Subtract 44. So 116 minus 44 is 72 degrees. These angles here are adjacent, but what else can I say about them? Oh, they add up to 90 degrees, right? That little square in the corner means they make a square corner. So if I call this x, that's telling us x plus 62 has to add up to 90. So we can subtract the 62 to get x is 28. 28 degrees. There's a special name for angles. If I have two angles that add up to 90 degrees, they're called complementary. Or sometimes called they're complements of each other. Now we're going to come across another word here in just a second called supplementary. If you're anything like me, and I had a hard time remembering which was which, is complementary 90 degrees, or we're going to talk about 180 degrees in a minute. Well, complementary angles form a right angle. They add up to a right angle or 90 degrees, and you get complements when you are right. So next, probably saw it coming, is a straight line. And if I have an angle coming off of that, if I know that one is 68 degrees, I know that x over here is x plus 68 has to add up to 180. So I subtract 68, x equals 112 degrees. I mentioned it earlier, when two angles add up to a straight line or 180 degrees, it is called supplementary. So what I've given you here is pretty simple so far, where I just gave you one of the angles and you had to use a simple equation to find the missing one like that. But it can get a little more complex. You might be told that this is 2x minus 5. And this angle up here might be listed as 5x minus 10. And the indicator here tells us that those two angles are adding up to 90 degrees, so they are complements. So what do I know about those two angles? Yes, exactly. They add up to 90 degrees. When we're dealing with geometric shapes like this, distances, angles, or whatever, we only have three possibilities. One, they add to a total, which is what these do. Two, they subtract to get a difference, to get a difference amount. Or three, they are equal. This is the first case. They add up to a total. So 5x minus 10 plus 2x minus 5 has to add up to 90 degrees. So before we can solve this, what do we have to do first? Combine like terms. 5x and 2x make 7x. We also have to combine the negative 10 and the negative 5 to make negative 15. The 90 is still untouched. So to solve this, our next step will be add 15. 7x is 105, and then divide by 7 gives us 5. This x equals 15, right? Now, if we asked what x is, we'd be done there. We'd be okay. But what if instead of asking for x, I asked you, what is each angle? We have to go back. This is 5 times 15 minus 10. So 5 times 15 is 75. Minus 10 is 65 degrees. This is 2 times x. That'll be 2 times 15 minus 5. 2 times 5 is 30. Minus 5 is 25 degrees. Does 25 and 65 add up to 90? It sure does. So let's take a look at this one. So 4x minus 8 6x minus 12. I want you to find the angles. In your notes, see if you can get that to work. So what's our equation going to be? Perfect. 4x minus 8 plus 6x minus 12 equals 180. So we're going to combine like terms. 4x and 6x make 10x. Negative 8, negative 12, negative 20. And then add 20. So 10x equals 200. And then divide by 10. So x equals 20. Now that's not the end of it. We still have to go back and find the angles. So 6x is 6 times 20 minus 12. 6 times 20 is 120. Minus 12 is 108 degrees. 4x minus 8, so that'll be 4 times 20 minus 8. 4 times 20 is 80. Minus 8 is 72. So 72 degrees. And we double check. Those two do add up to 180 degrees. So it works out. Another relationship we can have between our angles might look like this. So let's say I start out with this angle over here as being 38 degrees. What does this angle up here have to be? 142. How'd you get that? Yeah, this is a straight line here, which makes those two angles have to be supplementary. They have to add up to 180. So we just took 180 minus 38. Gave us the 142 degrees. What's this angle over here have to be? 38. Because this is a straight line here as well. So those two have to be supplementary. They have to add up to 180. So 180 minus 42, or 142, puts us back at 38 degrees. These two angles here that are formed on the opposite sides of intersecting lines have a special name. They're called vertical angles. I won't test you on the vocabulary, but you'll hear that term maybe used in the homework, so knowing what it is good. Vertical angles will always be equal. This angle and this angle will always have the same value. So if I have two angles set up like this, and I have 7x minus 18 and 5x plus 32, find those two angles for me. Give that a shot in your notes. See what you come up with. So 7x minus 18 added to the 5x plus 32. What's the relationship going to be? Equal to 5x plus 32. Those are vertical angles. They have to be equal. So now to solve it, we have an x on each side, so we have to get rid of one. We'll get rid of the smaller one, the 5x. So this is now 2x minus 18 equals 32 over here. What would we do next? Add 18. Make that look like an 18 maybe. 2x equals 50, and then divide by 2. X equals 25. So now we have to go back up and substitute in here 7 times 25 minus 18. Well, 7 times 25 is 175, and minus 18 is 157. 157 degrees. Down here, 5 times 25, plus 32. 5 times 25 is 125, plus 32 is 157 degrees. So they come out to be the same, so relatively assured that those were right. How many of you got 157 degrees? A couple of you? Okay. Well, there are some more relationships that we can talk about based on these. We talked about complementary angles and right angles. There's a term called perpendicular. And in 2 dimensions, on a flat piece of paper, perpendicular doesn't mean that much different than just a right angle. I mean, perpendicular means it forms a right angle in every direction. So 2 lines, if there's one right angle, the lines are perpendicular. So that means there's a right angle in every direction. There's 4 right angles. That's not such a big deal. But perpendicular is much more powerful in 3 dimensions. For example, if you pictured a line, bless you, a line coming out of the board at you or out of the screen at you, if it was perpendicular to the screen, that means no matter where you measured that angle between the line and the screen, it would be a right angle. That's perpendicular. Of course, the opposite of perpendicular is what we call parallel. Now, a lot of us have defined parallel lines as 2 lines that never intersect, which is okay if you're dealing on a flat piece of paper again. But let's say I have a line here and a line here. Do they intersect? No. Are they parallel? No, they're going very different directions, aren't they? They're not parallel. So the technical definition of parallel when you get into 3 dimensions is, the technical definition is everywhere equidistant. That just means always the same distance apart. Now, we talked about the navigational directions early on and how that used to be used to define angles. Another definition of parallel lines, again on a flat surface, is 2 lines going in the same navigational direction. And if we think of it that way, when we start talking about other vocabulary in a few minutes, it'll make more sense too. Then we have lines like this that are not perpendicular and are not parallel. Those are what we call oblique. On 2 dimensions, it does mean they are going to intersect, but as we just saw in 3 dimensions, 2 lines don't have to be parallel, and they don't have to intersect to not be parallel. So oblique lines are just any lines that are not perpendicular and are not parallel. Anytime I have 2 lines that I'm looking at, I take a 3rd line and cut it across those 2 lines, that 3rd line is what we call a transversal. To transverse means to cut across or to go across. A transversal goes across or cuts across at least 2 other lines or more. It's not very interesting when they cut across oblique lines. The power of a transversal really comes into play pretend those lines are straight and parallel when we have parallel lines. So if I cut these lines with a transversal, pretend that line's straight too. You got it? If you were in a high school geometry class, we would define all sorts of things like opposite interior, alternate interior, corresponding interior, alternate exterior, corresponding exterior, all sorts of different angles. And then whether they're equal or supplementary or whatever. But it's a lot simpler than that. When you have parallel lines that are cut by a transversal like this, there are only two angles formed. If I were to tell you that this angle here is 65 degrees, what's this angle here have to be? You got it, 180 minus 65, or 115 degrees. What's this angle here have to be? 115 degrees. What's this angle over here have to be? 65 degrees. Now this angle down here is a little bit less obvious. But if I happen to draw these lines close to parallel, this should work. If I slide this line down here and lay it on top of the other one, that angle is just the same as that one, isn't it? So this angle here has to be 65 degrees. Of course, that makes this one 115, and this one 115, and this one 65 again. So when you have parallel lines that are cut by a transversal, there are only two angles that are formed. So if you know one of the angles, all of the other angles are either equal to it or supplementary to it. That's all you really need to know. You don't need to memorize the opposite interior, alternate interior, and corresponding exterior, and all that. So if I give you that angle is 29 degrees, and I ask you for this one here, all you need to ask yourself, does that angle look like it's equal to it? No, it's not, right? So that's the only other possibility. You got it. Supplementary, there it is. So it's 180 minus 29, or 151 degrees. If it's not equal, it has to be supplementary. How about this angle here? Does that look like it's equal to the 29? Yeah, so it's got to be 29. All angles formed by that transversal over parallel lines are either equal to the one I know, or they are supplementary to it. In a triangle, the three angles have to add up to 180 degrees. Now that's only true for a triangle. If we get into other shapes, more than three sides, that's not true. But in a triangle, the three angles must add up to 180 degrees. So if I tell you that this one here is 72 degrees, and this one here is 68 degrees, this angle up here has to be 40 degrees, because they must add up to 180. So if I give you a triangle where I tell you this is 61, 72, what's angle x have to be? Well, x plus 61 plus 72 has to be 180. And we can solve it from there. 61 and 72 makes 133, is 180, and then we will subtract to get x by itself. X equals 47. So x is 47 degrees. Any questions? Okay. We can combine this with our parallel lines. Okay, so let's say that this angle right here is 34 degrees. And I'm going to tell you that this angle right here is 81 degrees. I want you to find this angle, those three angles, A, B, and C. So see if you can figure out what those angles have to be. So if that's 34, we know this one's 34, and this one's 146, and so on, right? Those don't help us so much. What does allow us to do is down here, what's angle A have to be? 34. That's on the same transversal as this 34 up here. So we know that has to be 34. Which means this angle has to be 34. Now, do we know either of these other two angles of that triangle? Yeah, we know this one has to be what? 81, because those two are vertical angles. So we've got 34 and 81. If I call that x for now, x plus 34 plus 81 has to equal 180. Yes, I do realize you could just do 180 minus 81 minus 34. That will work. Gives you 65 degrees. So that adds up to 115 equals 180. And we subtract. X equals 65 degrees. So if that's 65 degrees, that means B is 65 degrees and C is the supplement 180 minus 65 and 115. So it's kind of like putting together a big puzzle. Okay, it's about time for our break. We do have a couple of things left to cover after break. What I'm looking at is it looks like we got about probably 15 minutes or so of material to cover after break, maybe 20. And then since you guys are here on a night like this where nobody else is here and it looks like it's might be kind of snowy out, before I leave, I'll give you guys an extra credit question that you can work on and turn in next Tuesday. Okay? So let's take our break. We'll come back at 4:29 and start up again.